Set theory topic 3 kind of really brings it together and kind of starts mixing the notation with kind of some logic puzzles. And we got to get into a little bit of the math in our set theory here. It is kind of important to talk about kind of the big operators. We have our union symbol, brought to you by the letter U. We have our intersection symbol, brought to you by the upside down U. And we've got our not symbol, complement symbol. If I was to back that up just a second here and say our complement, but I really mean not, which is usually given with brackets, but we would put this little hash, this little prime symbol to indicate that we want something's opposite. We're going to play with these symbols to kind of get at very, very specific regions and describe certain things. And so I can kind of create, a diagram and kind of create a scenario that where this could be kind of relevant. So let me draw myself a little bit of a universe. And let me put, let me put 20 people into this universe. And in this universe, I'm going to have one set and a second set. And instead of actually just kind of writing in a bunch of individual elements, quite often in these diagrams, we kind of just include the total. So if I was to put 5 people here, 4 people here, and 6 people here, I could kind of just say that there are 5 elements, and then there are 4 elements, and then there are 6. It's just there's a little bit of a total. Now, one of the sneaky things that we sometimes do in these little logic puzzles is we kind of forget, not really forget, but we kind of purposely omit a number because maybe you already noticed, but I don't think I wrote 20 things. Where you just kind of sitting there being like, I think you forgot it. But where are those 20 things going to fit? And it only looks like I have 15. So, to build a full universe here, a truly good diagram, you want to just make sure that if there is any number being omitted or assumed that or you have figured it out, we would put that number on the outside just to emphasize. Now, we want to be able to access different pieces of information here. We want to be able to combine any 2 or 3 or 4, any combination of these numbers. We kind of want to come up with totals. And we can kind of ask this in a bunch of different ways. Now, in the simplest sense, we did this a little bit in topic 2, where I could ask things like, well, how many things are in A? And how many things are not in B? And in this set notation, we would kind of make these queries. And there are maybe a couple numbers to combine, and there's perhaps a little bit of just natural adding involved in when we kind of do this. But as I kind of like to do here, the number of things that are in A is kind of requiring you not to just focus on that 5 there. That there's definitely 5 things in A, but A, the set called A, does include the entire circle, the entire set called A, which has already been split and organized for us because there seems to be four people who are maybe in both groups. And, those 4 people are definitely a part of A. Just because they're part of something else doesn't mean they're not in A. And we do want to include them. And so this would kind of, add up to 5 plus 4. And we're not adding the same stuff twice. We're just kind of taking a natural total here. That's how many things are in A. Now, that's not the same as saying you're not in B. In fact, that's one of the first little logic puzzles here. Is being in A the same as not being in B? And absolutely not. These are not the same thing. And I'll show you why. Not being in B means that we're excluding anyone who potentially is in B, but we've got an entire universe to essentially kind of take into account. And so this entire region, everything excluding that little region we call B, is called the complement, the not in B region. And again, that's not just the 5 people. I mean, it does include those 5 people are not in B, but it also includes those 5 people who are on the outside. And this kind of comes out to 10. So we have just some smaller sets like this. But once we start getting into our union and our intersection, we can start making these asks a little bit more intricate. Now, some kind of key talking points here about union. Union on itself is asking you to take the total. In math, totaling something up is also equivalent to saying, I want the sum of things. Union also is connected to the word or, means the same thing mathematically. I want this or this. It also means the same thing as adding, which is also, the same thing as sum. But one of the things that union is going to do for us is that it keeps, it keeps building, and there's nothing that gets omitted. And so nothing in a union you're pointing to right onion, but nothing in a union is excluded. And we'll talk about that more, but unions get really, really big. It keeps on adding more and adding more and adding more. Anything that's described is going to be included in the total. And so we are just kind of looking for a really large total, which is kind of separate and actually quite different than, say, when we intersect something. Intersections ask for kind of a different thing. Some of the key words that we work with intersection will always be connected to the word and. And it's definitely part of a scenario where we have to look at the overlap, where things have to both be true. And the key distinction here is that it definitely excludes all elements that aren't a perfect match. Because we need everything being asked to be true, not just some of it to be true. In a union, any one thing can happen and you're in. Any one thing can be true. You can fail 10 times, but as long as you get one thing right, you're part of the union. But in an intersection, you got to be all perfect. It's got to be in a very, very overlapped position. As you know, in the future, I mean, there is no multiplication in this unit. I mean, we're only looking at diagrams and trying to total things up, essentially. But in the future, and will almost always be connected to the multiplication of things. In probability, in counting methods, intersections kind of means that we're going to be multiplying things together. But I promise you, in this first set theory unit, we're only adding and subtracting. We're not multiplying to create numbers here now. We're not working with probabilities. So let's use some of this information in a real way. So, if I started asking questions like, and let me just kind of move some of this over a little bit. How many things are in A union B? How many things are in A intersect B? We start getting into a little bit more complicated totals, or at least where we have to pay attention pretty carefully to this. Here's our or, here's our plus sign, here's permission to collect everything. Everything in A plus everything in B. It's all coming. It's all being included. Union is a lover of all, and it is collecting everything that we can. And when we start doing these kind of calculations, unions, intersections, this is where I really do think the diagrams become quite helpful to keep our kind of sanity and kind of try not to overthink things. But let me put a check mark in all the regions we're calling A. And that is set A, as I'm looking at that diagram up above. And so, we've already got them. There is no reason I would ever get rid of those things because they're a part of a union. We're stuck with A. Now I'm going to put, say, I'll put a little box next to every region that I'm calling B, because B is coming too. We're supposed to be adding B and A together. Here are all the things that I would consider to be a part of B. Now, just because something is counted twice doesn't mean that we have to now just like get rid of it. No, that's fine. Just because you got two, it was true for both of them, that's fine. We're just adding these together. To me, a union is almost like an invitation to a party. Remember what those were? Getting an invitation to a party. And, I want all of A to come to the party. Maybe it's everyone from my anthropology class. Or I'm going to invite everyone from my biology class. And I want to have a huge party. Now, some people might get 2 invitations because they happen to have been in both of your classes, but they're still coming. Just because they got 2 invitations doesn't mean they're going to get offended or anything like that. So what I'm looking for here is I'm taking A plus I'm taking B, and I'm just being careful that I don't add the same thing twice. I mean, it would be kind of a big mistake to think that, well, hey, I see 9 things in A. Oh, I see 10 things in B, and that adding them somehow come out to 19. No, that's actually counting the same stuff twice. That's not good logic. This comes out to 5 plus 4 plus 6, which is a true total of 15. There are 15 things in A or B. Union. Nothing was excluded. Everything was collected. It was a grand total. We summed it up, and we took as much as we were allowed to, as much as we were asked to. Nothing more, nothing less. The union versus the intersection. Here is our and symbol. Here is where it has to be an overlap. Here's where it has to both be true. And so this is, instead of collecting all of the information, we're actually excluding most of the stuff. Intersecting is a way of getting rid of noise. Okay? Instead of a party, I think of intersecting more like when you're hiring somebody. That, just because someone is, ambitious doesn't make them perfect for the job. And you need them to be, say, book smart or something. And just because they're book smart doesn't make them good for the job. You need the perfect candidate. You need both, or else you're not interested. And so let me kind of do the same kind of operation here. It's going to look very similar to what's up above, but here is A, here is B. Here are the people who are in A. Here are the people who are in B. Is there any place where they were perfect for both, where there was an overlap. And in this case, yes, this is a really, really common intersection, but here is my overlap where they were both true. It wasn't a lot of people. I am literally excluding. I'm saying, nope, that's not good enough. Nope, nope, none of that. It's a way of excluding all that noise, focusing in on a very specific overlap. And I mean, half of these times you don't even have to add stuff because it's so limiting. There's really only 4 people left after you've gotten rid of people who didn't meet all of your criteria. And so we kind of get those intersections. And this is when it gets good. This is when it gets really good. Diploma level at standard. How many people are in A union B prime? Ooh. How many people are in A prime intersect B? Think about that. This is not straightforward totals anymore. We're getting into some legitimately good puzzles. And we're really, really getting into some technical notation here and not just asking a straightforward region, not just a straightforward intersection. Going back to my strategies, and that's where I can kind of, figure this out. Even if I have no idea where to start, part of doing a puzzle is trying something else, process of elimination, and just logically sorting it out in some sort of strategy, and just hopefully you get there. Hopefully you don't get frustrated and you don't kind of just say, I can't do this. But going back to basics, I'm going to put a check mark for A. I'm going to put a check mark if we're not in B. Actually no, I won't go there yet. I'll put a little box if I want B. If it's not in B. So hopefully you agree with me here. Here are the things that are in A. Here are the things that are not in B. You agree? Union wants us to collect it all, add it up. We're taking this, and we're taking this outside region. This is what all of A plus all of not in B looks like. And I know there's usually some questions here to say, it says we're not supposed to take B, but then why did you take this region? That section is in B. But that doesn't concern me. That was a valid region in A. This statement does not exclude stuff that we've previously taken or that we might take in the future. That's not the job of a union. Union says no to nothing. It says yes, yes, yes. This is the yeses from the first statement. Here are the yeses from the second statement. We're taking it all. Union takes everything mentioned as the total. And so logically, realistically, I mean, these were the only 6 people I was not interested in, and that takes me down to 14. All of those sections have to add up to 14 when I take my total. And in this intersection problem, this is where I get to eliminate a lot of different things. Like things that are not in A. Yes. Those are the regions that are not in A. Okay. Here are the regions that are in B. In B. It's not B prime. It is B. In B. Yes. Yes. Now, do you see the overlap yet? Do you see where they are both true? And in simple speak, where there are both symbols? It's not in the middle anymore, because that's not what they're asking for. It's still an overlap, but this is the overlap. This is everything that matched. This is the perfect space that made everything come true. Because if I read this in English, it has to be not in A, and it has to be in B. Not in A and in B. Well, that's the only region that matches all that then. It has to be in B, but it can't be in A. So it's essentially, quote unquote, it's only in B would be another way to describe that. And that has excluded, nope, not good enough. Nope, nope. Excluding most of the diagram, the only region actually is those 6 people, and that is the intersection of not A and B. And so we start playing with these symbols, and we start giving you different puzzles to kind of worry about. So now that we got that out of the way, what's fun in this topic is building your own. Let's build our own. Your job is to logically sort this information into a diagram. And, on an exam, in a realistic scenario where we're kind of testing this concept, we would ask something about it. We would ask, for example, how many people play, I don't know, how many people don't play hockey? Just something nice. Or how many people play squash and hockey? Now, these are good questions. And if you don't know kind of where to start, it can get kind of frustrating. It can get kind of tricky. Now, realistically, if we were to go explore all the options, perhaps this diagram would be drawn separately. Squash players and hockey players are totally different groups of people. Maybe it's this situation where some people play squash and hockey. Maybe there's people who play both. I mean, if I was to go through all the scenarios, maybe all hockey players are squash players. And then it's a subset. And these are some of the combinations that we could possibly draw here. Now, by process of elimination, we can kind of rule some of these out. It can't all be all 3 diagrams. Mathematically, logically, there's only one way to do this. Now, watch what happens if I say just try to build a disjoint. What's possibly wrong with putting all 15 squash players here, all 8 hockey players here, and 6 people who play some other sport, chess. I don't know. Is there any problem with that? Is there anything not logically correct with this diagram? Hmm? Hmm? And so, did we actually keep the universe as it's supposed to be? I don't think so. 15 plus 8 plus 6 is 29. This seems to add up to 29, but I only have room for 25. This is kind of a big, pretty big red flag, and say like, I don't know if that's supposed to be what's going on here. Maybe it's like this. And let me do this logically. With 8 people who play hockey, that only leaves 7 people who could play squash, because now that adds up to 15 squash players, and then there's 6 people in another sport. Now, does that add up to 25? Is there anything misleading about this organization? And absolutely, this only adds up to 21. And again, that's another kind of big fail. And so, process of elimination, this is most likely the most reasonable way to organize, where there are some squash players, specific, there are some hockey players, very specific, and there's probably people who play both, plus all these people who are playing some other sport. There's probably people in every one of those sections, and we probably, like all good math questions, want to work inside out, brackets, and then work our way out. It's like the bedmass of logic. Let's figure out the middle first. And this wasn't really a bad idea to kind of go through this scenario, because those 2 other diagrams are kind of giving me a little bit of a clue. In one case, let's get rid of that. In one case, I'm 4 too high. And in the other case, I'm kind of 4 too low. And this is kind of trying to hint, it's like a little bit of the universe kind of speaking to you to say, I don't think I need to guess how many people play both sports. I feel like something is there is a sign here. I feel like we can kind of go off and be a little bit risky here. Let's put 4 in the middle. 4 people play both. Let's see if we can make this work. We've got my squash, got my hockey, and we've got our 25 people who are in this class. Not one more, not one less, exactly 25. Classic mistake. People put 15 here. No. That's not 15 squash players anymore. That might say 15 people who only play squash, but that's not saying 15 squash players. And this says that there's 15 people who play squash, not squash only. 15 people play squash. So, we got to be a little bit smarter about that. Nope. Now, 15 minus the 4 people who we are already tracked down and already put down on paper leaves me the 11 supposed people who only play squash. And that is definitely 15 people who are playing squash now. And given that there's 8 people who play hockey, I'm not going to put an 8 there, because now I'm way over 8. That's not 8 people. This is 8 minus 4 leaves me 4 people who now only play hockey. With the 6 people on the outside, is it gonna work? Does 11 plus 4 plus 4 plus 6 equal what we need? Boom, boom, beautiful. Checked. That is our diagram, perfectly organized. There is not another way to draw it if we are following the logic to a T. How many people don't play hockey? I'll show you who. These people don't play hockey. They love their squash. These people also don't play hockey. They love their chess. And there's my total. Or at least there's the regions that are all about not being in hockey, which is those 11 plus those 6, which comes out to 17. How many people play both squash and hockey? Well, I'll show you again. Here are all the people who play squash. Here are all the people who play hockey. Can you see the overlap? It's right there. This is the one section of people who play both, who it's true for both. Intersection has to be overlap, and that is according to our little diagram, at least the correct diagram, came up to only 4 super athletes. And that's kind of a rundown of topic 3.